We have been working in developing a platform that we think it's a nice idea and will be very useful, and we wish it will be used for many users around the world. This is our dream. And maybe you will be in charge of maintaining that platform, and might be, or actually I hope that it won't be a nightmare for you. So with this in mind, I would like to present you ICIQ, that is a web platform to do things after computing. Because after computing, we also have problems. And okay, maybe it's not necessary to introduce you in which field I'm working on. So I'm a computational chemist, and nowadays in many fields of chemistry, also as well as in the past, HPC is used massively, and now we have reached a point that we really can solve real chemistry problems. And most of the times we work very closely with experimentalists, with chemists that work in the bank, and we try to tell them what they are doing in the flasks. Not only that, but also we are trying to understand how chemistry works, how can we design new molecules, new catalysts, new materials to solve society problems. Okay? This is our main and final goal. And actually this field has been awarded with Nobel Prizes several times. Last year, 2013, was the last one. And this, I'm using this picture from the Academy, Nobel Academy, that really describes well what is our field nowadays. So we are turning this never-ending cycle, working in the labs, the chemists work in the labs, and we try to help them, and this retro feedback is never-ending, trying to improve new chemistry. And in some fields, in chemistry, especially in catalysis, catalysis is crucial for improving industrial processes, to make them greener and more efficient, to make fine molecules useful for health. Okay? So in some fields, for instance in this one, the explosion of papers published regarding research has grown in the last years, and we start facing the problems of permanently storage the results we are producing. So what to do after the calculations? We must store results. This is one need. We are also facing problems relating to the certification of results. With this explosion of papers published, this means that there are lots of groups around the world working in these fields, especially in South Asia, and especially in China. And there is no way nowadays to certify that the results that one research group publish are true results. I don't know what, I think that you understand what I want to say. Okay? It's, sometimes we have doubts about the results that other people publish. Okay? So it's important nowadays to have means to certify published results. And also, it becomes almost an absolute need, and also facing the research projects in the European Union to be able to reuse results. So here, open data is an important point. Get results, doing research, but then make those results publicly available. Okay? So we have several problems, and we think that our problem is a big data problem. And the first problem is these two pictures taken from our lab that reflects quite well what is on here. So there are some people that is quite ordered, working. They have a clean table. Many times they are using just a piece of paper and a pen to to take notes of their research to extract the main results. This is how we still work today. Okay. There are some notes over there. There are other people that are a mess. There are a mess on the table. There are lots of papers, photocopies, notes. Okay. Maybe this guy here is well ordered outside, but maybe it's not well ordered inside the computer. There's a mess of folders, files everywhere, file names impossible to understand. Maybe they are noted in a piece of paper, but the files are there, the files that we produce computing. And maybe this other guy is the contrary or not, it's even worse. Maybe it just has just only one folder with thousands of files there. Okay, so this is first problem. Second problem we face is storage. Okay, we have racks, we have terabytes, petabytes of storage, but at the very end, we keep hard disks, we keep CDs, we keep pen disks, named with the people that produce those results, those files. Yeah. And in our particular case, our research groups are quite dynamic. So we have PhD students working with us. Normally they spend 3-4 years in the group. Then we have postdocs that just come for 1 year, 2 years. And all these people is moving and continuously changing. So we must keep records of the production that those researchers have been done during their stay, and probably will need to continue those research projects in the near future. So this is the second problem. And third problem relates with publishing results. I don't know if you are well aware of how we publish results in scientific journals. So this is a manuscript with text and tables. It's a PDF file. And then we add normally what we call the supporting information files. And supporting information files nowadays are as well PDF files, like those images here. So lists of numbers in our case, just coordinates of the chemical system, maybe some picture, maybe some other data with relating to energy or properties we computed. And maybe we spend weeks to compute one of these geometries. And at the very end, this is published, but it's published just in PDF files that are uploaded to the editorial. Normally are publicly available, but it's quite difficult to read them again and to know what is exactly that information. They are not certified, and the problem is precisely to reuse and to look for those files. So actually nowadays it's impossible to find any of these files looking at Google, for instance, yeah, for what is supposed that they contain. Okay? They are not indexed. They are available on the web, but are not indexed in any case. So yes, we think that we have a big data problem, and this is why we thought that we should do something, and this is what ICIQ tries to deal with. On the other hand, when we talk about open data nowadays, the standard, the direction was fixed by this guy that you know very well. And this guy talks about stars of a quality of data, having 1 star till 5 stars. Today we are in this at this level. Okay, files are available on the web as PDF, plain PDF files, not indexed, or maybe in some cases, Excel or other type of format. The ideal would be to have the data in well-defined formats, well-indexed, well-linked. Okay, so our aim is to jump chemistry data from this low level we are right now till the top. Yeah? How we work nowadays. So at present, we use HPC, we submit jobs, and we generate terabytes of data, if not petabytes, but a lot of information, a lot of files. We need to scratch, disks, we need everything. Huh? Maybe you know that that computational chemistry has been one of the stronger users of HPC for many years, and is still. So we are generating actually maybe 95% waste in your systems. We are filling your disks with waste, because only a few percent of the results we are generating are useful and deserve storage, permanent storage. Okay? This data is then collected almost in all the cases manually by the researchers. From this data we elaborate reports, almost manually, and these reports are then uploaded in public HPC for sure, but maybe the cloud, who knows, depends on the cost. Okay. These results should then be automatically incorporated in databases. This should be known when you submit a new job, in order to not to repeat the calculation if it's already done. Okay. And all this data should be well linked, and the researchers finally would have, or should be able to have reports generated automatically that then would be again published. But if these databases here in between exist, then the information that the publishers can access is richer, okay, makes sense, is indexed, is real information, not just data. Okay? And in that way, public has access to information, but most importantly, public has access to the files. They can check the results, they can reuse the results, reproduce calculations. Okay? This is one option. Yeah? Our platform at present is not fulfilling these demands, but just only wants to create these databases, automate some processes, and have or give people access to our results. Okay, that we are on that way. So what's ICIQ BD? So actually ICIQ BD is two tools. One is just a repository, a public repository to store and to access information, but also a tool to manage the results from our jobs, inputs, outputs, and outputs. Okay, and it comes so to fill that gap and to raise data to 5-star quality. And it's started independently in two institutions, both in the same campus in Tarragona, the ICIQ and at the university, and finally we merged those two projects, and a new baby was born. Yeah? The goals of this project is to build a very big distributed database of results from computational chemistry, actually reduce the storage, reduce the size of the information we keep, but also increase the value of the data. We are committed to use standard formats, XML and CML, which is especially chemistry markup language, with the tags we need to label our data. We want it to be a daily tool, not only temporarily or occasionally, a daily tool for data management and to manipulate and search. In this way, we think that we are redefining workflows of how we store the results and how we will publish our results, going to open data. And also it's a platform, flexible and open, that enables to add other functionalities and other tools quite easily. Okay, it's a web platform quite flexible and using modern technologies. An important tool for the chemist is that you can search the data by using chemical subtraction, so making drawings like chemical formulas. You can make queries from there. And maybe to go a little bit more inside the architecture, and if this works, I can show you a little bit this graph. Okay. Okay, it's several modules and several servers. Actually, there is a central authentication system that loads the user or logins the user in the two main servers. One that is the public part that is open to the internet, and the other is a private server. These servers are fit to extract the data we generate, so input and output files, are converted to XML and CML by using XSLT. XLT templates that are used both to define the extraction processes, but that also use then to define how the data we extracted are represented or just displayed. And what else here? Okay, the substructure self-service is provided by external software that is provided by Chemaxon, for instance. Yeah. And finally, not yet implemented, that is our goal, the public servers should be synchronized and syndicated in a big cloud containing all the metadata and maybe the data as well. Yeah. So, going back here. Regarding the data extraction, there was a problem initially because we use a system of routines called jumbo converters that was used to extract data and convert it to CML, and that was quite inefficient. And Moises, who is sitting there, reprogrammed these libraries, and using Saxon, that is a special XML library, we really improve the performance of the transformations by orders of magnitude. So our system is much faster than initially. And we use this scheme to explain what IOCMBD is in an easy way. So I just told you that we have two servers, mainly two servers. We call one create and the other one browse. Create is used to upload, convert, and store and manage the data. And finally, browse is a server that enables publishing. Create has two interfaces. Obviously, a web interface. It's like a desktop application, almost. And a plain shell interface. We are still tough users, and we still use shells all the time, as 20 years ago. Things never change. And with these two interfaces, we upload, we convert, and we store. At this point, we can validate the results, we can check whether the results, whether the programs finish well, for instance. Sometimes a calculation doesn't converge, it finishes, but the result is not correct from an expert point of view. And at this point, we can check whether those results are good results. Okay. This is a view of the shell interface. It integrates perfectly and without troubles, into any Linux shell. And we have a series of commands to start, to log out, to list projects, to create projects, create files, upload files. Just additional commands you will find in the shell. And this is the look that the web interface. So we have here a panel with files, folders, and projects, some metadata associated with schedule calculation, and the same point we can visualize the chemical structures in 3D, and move and analyze, and so on. Yeah? So once we have uploaded the results, we can use this application, this desktop application, this web interface, to manage results and even to treat that data, to process that data, to make additional numerical treatments, for instance, that sometimes are tedious. And this is one of the cases that we used to generate this sort of plots. These sort of plots nowadays are done manually, just extracting the data manually, inputting in some Excel, for instance, Excel data sheet, and then plotted. So we can generate this sort of treatment automatically, and this is a very useful tool for chemists and for researchers. And what's also very important, we can generate automatically those PDF files. Obviously, we have the data, we can select which data we want to publish, and automatically generates reports. And this saves a lot of time, in our opinion. And once we have finished a project and we have all the data uploaded in the database, then we can publish that data. And this is the task accomplished by the module we call browse. And this generates URLs and can be linked to a published manuscript, and is a public web server where people have access to. The first server is private, okay? It's intended to work inside an institution, inside research groups, and the second is the public access server. And it has a much plain look. It's actually, browse is a DSpace repository, okay, that we have tuned to fit our data, to generate metadata, and so on. At present, we have some servers up and some demo servers, and if they have 5 minutes, I will try to connect to. We are supporting almost, or very well, 4 of the main workhorses in computational chemistry. We are now, and this is true, this is actually almost true, this is our task this week and the next week, to final test of integrity, that checking every field we capture and how we display it. The reports module is not yet finished, but our goal is to have a first release to public by the end of this month. Yeah. And the future is a long list of things to do. We plan to design a way to syndicate the different browsers and the different databases, maybe using a central point. We plan to connect our data with other databases in chemistry. For instance, the Royal Society in Chemistry in the UK have a very good product, and it's called ChemSpider. So we plan to connect with ChemSpider, but also let ChemSpider to connect to us. Okay. So the future, I think, will be very funny. And I'm finishing just thanking the people who is doing the job. Actually, the main architect right now and that has been working since the very beginning is Moises, that is sitting over there. So you have questions. Probably Moises is the authoritative person to answer them. Yeah. And I thank all the institutions that have put monies along these years to support this project. Yeah. And if I have 5 minutes.
Yeah. Yeah, I think at this point we're late, so
Yeah, we're late.
yeah, it's important 5 minutes more.
We'll try to make a live connection and to show you how it works. Oops. Oh, yeah.
Oh,
Te la dic. Abans estava a l'Edurom,
que estava millor.
però ara veig que no veig ni...
Espera't que et passem dades.
Mira,
L'identificador, Barcelona, Navarra...
Dic jo?
Vale.
Aquests dies
És que va millor l'altre, eh?
Ok.
Ja està.
Sí? Ah, però tampoc.
Okay, here you find our main site, the different instances that are running, and these are real production instances. This is a demo server that you can access to, and okay, here, and you can log in to the create. Moises, this is giant. I don't know why. It's the resolution of this screen.
Yeah, this is...
Yeah, it's
You
probably
can-
Scroll down.
it is. Which one?
Music.
Scroll down.
Eh?
The demo users.
Right? Quina?
Suposo que és 1024 per 768. El que passa que la... Bueno, sí, una...
Okay. No, more or less. So you have here some demo users and passwords you can use. Okay, so this is create application. It's like a desktop application. You can move and navigate through your projects and watch your calculations. Okay, and expand everything, and automatically you get a preview of the molecule that you computed, and you select a job. Then you see this part of the window. You see the 3D structure. You see the summary of the main results, so of the fields which we captured from the wall output file, geometries. Yeah, here we have some data associated to the user, permissions, and so on. You can view the results full screen, okay, to analyze them, or actually download the results, the input files we uploaded or we downloaded. We can see the true CML if we like. Okay, this is a chunk of data that we created, but this is perfectly tagged, perfectly labeled, and now this data makes sense because we know exactly what does it mean. Okay? And we can switch what we have here for this, some files and projects. We have already a handle and a label that these files were published to the public server, which is browse. So we can jump to browse and see there the files that people uploaded with the data, metadata, and so on. And I think that this is all what I wanted to show you. Thanks for your attention.